Hi, I'm going to talk about our paper, Taking a Hint, How to Leverage Loss Predictors in Contextual Bandits. My name is Chen-Yu Wei, and this is joint work with Haipeng and Alekh. We consider the contextual bandit problem. Here is the setup. In each round from 1 to capital T, first the environment choose a context xt and a loss vector lt, which is a k-dimensional vector. The learner observes the context xt, and based on the context, we choose one action, at, between 1 to k, and observes the corresponding loss, lt of at. Notice that the classic multi-bandit problem is a special case of contextual bandit, where there is no context. The policy pi in contextual bandit is defined as a mapping from context to actions. And suppose that the learner is given a fixed policy set, capital pi, then the goal of the learner is to be competitive with the best policy in capital pi. Formally, we can define the regret as the difference between the cumulative loss of the learner and the cumulative loss of the best policy. The minimax regret bound for contextual bandit is square root kt log size the policy set. And in this talk, we will view the number of actions, k, and log the size of the policy set as constant, and simply write this bound as square root t. The tight bound is achievable with the classic algorithms exp4 and ILOC2 bandits. In this paper, we ask the following question: can we do better when the losses are predictable? By predictability, we mean that before the learner chooses actions, they actually obtain some knowledge or side information about the loss vectors. So we consider the following slightly different setting, slightly modified setting. This protocol is similar to before, but in each round, there is a loss predictor MT, and this is revealed to the learner before it chooses the actions. The hope is that if MT is close to LT, the regret bound may be much improved. Here we give some examples of this loss predictor. It can be some regressor that takes context and actions as inputs and output a value of loss prediction. This regressor could be fixed or learned on the fly. And in the multi-bandit special case, if the loss sequence is slowly changing, previous work also considered MT as the average of the losses in a recent window. So the key question we ask is that if the total error E, which is defined as the sum of the squared error between LT and MT, is small, can we improve over the square root T regret bound? And notice that this E is always upper bounded by T. This problem has been studied before in the full information setting and the multi-bandit setting. The bound they get is square root E, so this bound scales down smoothly when the total error decreases. For contextual bandits, a closely related topic is doubly robust methods that use loss predictors, loss estimators MT to reduce the variance of policy evaluation. However, predictors in the online exploration scenario was not studied. And before showing our bound, we further introduce a more general setting that is considered in our paper. And this protocol was similar to before, but in every round, the learner receives m different predictor. And we ask the following question. Suppose that the best predictor has a small total error E star, can we improve over the square root T bound? And again, this was studied in multi-bandit and full information case. In these settings, one can get a regret of square root E star plus log n, meaning that the price of learning over predictors is only logarithmic in the number of predictors. And now we see the overview of our results. When there is only one predictor, and when the loss total error E is smaller than square root t, the tight bound is square root E times t to 1/4. And when the total error is larger than square root t, the tight bound is simply square root t. This means that one can only improve over the minimax bound square root t when the predictor total error is smaller than square root t. This is a sharp difference with multi-bandit and full information case, where square root E is always possible for all values of E. We also found that the above tight bound is achievable only if the learner knows the value of E. If it does not know E, we show that the same bound is not achievable. Again, this is very different from the multi-bandit case, where one can achieve the tight bound without knowing the value of E. And as a remedy, we show that in this case, a slightly weaker bound is achievable. That is square root E times t to 1/3. And for the multiple predictor case, again, different from multi-bandit or full information case, we cannot get logarithmic dependence on n. Instead, our lower bound shows that a linear dependence on n is unavoidable. So you can see that all these results shows that the contextual bandit case is very different from the settings that multi-bandit or full information settings that we studied before. And finally, for all settings, we develop general algorithms that work for the case of adversarial losses, and ERM or coefficient algorithm that work for the case of IID loss sequence, which will be clear later. And in the next section, we will focus on the technique that we use for single predictor adversarial case. Our algorithm is built upon the classic contextual bandit algorithm called EXP4, which performs exponential weight updates over the policy space. To incorporate the information of the predictor, we use the standard technique of optimistic prediction. So when the learner receives the predictor at that round, he first makes an update based on predictor. Also, the loss predictor fed to the algorithm is a variance-reduced estimator centered around MT. This algorithm, if following the standard analysis of exponential weight, one would expect to get the following bound. And suppose that you can get this bound, then taking expectation and pick the best eta, you get the square root E bound. However, as our lower bound shows, this is not possible. So there is something wrong. And the caveat is that to get this bound, we require that LT minus MT should not be too negative. And so this was not an issue in the standard EXP4 when all losses are positive, but becomes an issue in our case because LT minus MT might be negative. Now, E fix to this issue is to enforce an uniform exploration. However, with this fix, the regret would be at least square root t, and our goal of improving over square root t would be impossible. So here we present our solution. In the beginning of each round, we define the baseline action AT star as the action that has the smallest MT. Then we define the active set, capital AT, as the set of actions whose predictor is no more than the baseline plus sigma. That is, the active set is the set of actions that look not too worse than the baseline action by the amount of sigma. Then we can define the action mapping phi t. This phi t maps all the actions in the active set to itself, but maps the actions outside the active set to the baseline action. Now with this action mapping phi t, in all the following steps, we pass all the actions through this mapping. Equivalently, if a policy originally select an action A, you can view that this mapping redefines the policy so that it selects an action phi t of A. We can see that the whole algorithm will not select any action that are outside the active set. The intuition behind this action mapping is very simple. First, we see that by the definition of the active set, it will exclude actions whose predictor MT are bad. That is, the MT of A is large. Then, because the error is small, we can infer that the loss of the actions outside the active set is also large. Then, because of this, it suffices to explore the actions in the active set, because the actions outside the active set is expected to be bad. And because we restrict the set of actions that we explore, the regret overhead would be reduced compared to the standard uniform exploration. Okay, then next, we briefly describe the design of Oracle efficient algorithm for the IIT setting. First, and if Oracle efficient contextual bandit algorithm assumes access to the empirical risk minimization oracle, which finds the policy that minimizes the total loss of a set of contexts and loss pair. Our algorithm is built upon the basic contextual bandit algorithm called epsilon greedy, which is Oracle efficient. The epsilon greedy algorithm at each time calls the ERM oracle once and finds the ERM of the loss, finds the empirical risk minimizer of the loss estimators in previous rounds. Then at round T, it follows ERM with probability 1 minus mu and perform uniform exploration with probability mu. In our algorithm, we have two modifications. The first is that instead of finding the ERM, we find the policy that has the smallest Catanese estimator. The Catanese estimator is a kind of robust mean estimator, which gives an estimation of the mean with an improved concentration bound. The second modification is again the action remapping scheme that is exactly as what I described before. With these two modifications, we can get the type down. And notice that to find the minimizer of the Catanese estimator, we can approximate it by calling the ERM oracle log t times, which makes our algorithm oracle efficient even if we only have the ERM oracle. And to summarize, we initiate the study of online contextual bandit with log predictors. For the single predictor case, we give a complete answer about lower bounds and upper bound. And we show sharp contrast between contextual bandit and multi-bound bandit or full information setting when there are predictors, including that the regret dependence on the total error and the regret dependence on the number of predictors, and whether the prior knowledge of the total error E matters to the learner. Finally, we are also curious about the empirical performance of our algorithm and how can they be applied to real systems and their future work. So that's it for my presentation. Thank you for your attention.